Hey everyone, and welcome back to this class, Deep Reinforcement Learning, Deep Learning in Python Part 7. In this lecture, we're going to look at the code for nets.py. This code is relatively simple compared to the other files in this example, since it only involves building neural networks, which we already know how to do. The most challenging part of this will be to get the policy network and value network to share their parameters. So the first function we have is for building the body of the neural network, called buildFeatureExtractor. You won't be able to tell just by looking at this code, but this will allow us to share these layers between the two networks. So this is going to be a standard convolutional neural network. First thing we want to do is scale the inputs to be between 0 and 1 by dividing by 255. Next, we pass the input through two convolution layers. Then we flatten the data and pass it through one fully connected or dense layer. So pretty basic LeNet style architecture. Next we have the policy network class. In the constructor, we're going to take in the number of actions as the number of outputs and a regularization constant. Next we're going to create our placeholders. The first placeholder is our input data, which is, just like with deep Q networks, a sequence of 4 consecutive grayscale frames. The second is the advantage placeholder, which will contain a batch of advantages. The third placeholder represents the actions that were selected for each of the input states. As you may recall, this is all the same as we discussed in the policy gradient section. Next thing we're going to do is pass our inputs into the body of the neural network. To do this, we're going to create a scope called shared and set the reuse argument to false. Take special note that this is false, since it'll become relevant later in this lecture. So we call buildFeatureExtractor, and we get out a variable called fc1. The next thing we want to do is pass fc1 through the rest of the neural network. For us, this is just a single final dense layer, which maps to the action space. More precisely, we're going to get the logits for each action, after which we can apply the softmax to get the probability for each action. As usual, the next thing we need to do is build up our cost function and then create our minimizer. Of course, creating the minimizer is not so simple in this case because we know that the gradients for the worker networks will be used to update the global network, but more on that later. In terms of the output and cost, there are still a few things we have to do. First, we need a way to sample an action, given the output of the neural network. Luckily, TensorFlow already comes with a categorical distribution object, which accepts logits as input. We can create a TensorFlow tensor called sampleAction, and then use that later to sample actions. So that's what we're going to use when we're playing the episode. Next we have the entropy term, which acts like regularization for our model. Next we need to select the probabilities for the actions that were actually selected. Unfortunately, this isn't as clean in TensorFlow as it would be in Theano, but we can still make it work. As always, you can always explicitly output NumPy variables at each step in order to get a better idea of how each operation works. Finally, from the selected action probabilities and the entropy, we can calculate our loss. The next thing to do is write some code to help us minimize this loss. First, we're going to create the RMS prop optimizer, and then we're going to use it to compute the gradients for each variable in our network. Next, we're going to do something which is unusual that you won't see in our normal single-threaded scripts. Instead of calling the RMS prop minimize function, we're instead just going to get the gradients and their corresponding TensorFlow variables. And for now, all we're going to do is store this list as an attribute of the network. You'll see how these are used later when we actually do the update. Next, we have the value network, which is largely the same thing, except it predicts the value function. First, we only have two placeholders, one for the input states and one for the target values. As before, we have 4 consecutive grayscale frames for the input. Next, we're going to create the initial layers of the neural network. Importantly, we are again going to use the scope shared, but now we're going to set reuse equal to true. This is important because previously we set reuse equal to false. That means when we call this function build feature extractor, it's going to use the same variables we created previously. In other words, it's going to share the weights for those layers between these two networks. And so this effectively makes the body of the neural network shared between the value and the policy, just like we discussed. Next, we create the final layer of our value network, which is just a fully connected layer with one output. We'll call this v-hat. We also need to convert this into a one-dimensional tensor, so we use the squeeze function. Next, we're going to calculate the loss, which is just the squared error between v-hat and the target. Finally, as before, we're going to create an RMS prop optimizer, but instead of calling the minimize function, we're simply going to obtain a list of each variable and its corresponding gradient and store these as an attribute of the object. The last piece we have in this file is a function called createNetworks. So the way this is structured is that to create a policy and value network, the other Python files should only use this function. They should never individually create a policy network or value network. And the reason for this is the policy network always has to be created first, since it sets reuse equal to false, whereas the value network sets reuse equal to true. So in order to avoid ambiguity, any outside code wanting to create policy and value networks can use this function. In the next lecture, we'll look at the final code file in this example, worker.py.